doesn't wash. So the next thing, and I think, is maybe arcsine. Now, first thing I guess I need to understand, when you guys do an arcsine, is this or this what you were taught in Miss Karen's class? Does that either one of those look familiar? One, okay, good. That's far more common. That's the way I would definitely teach it. Good. All right. This is how the book poses it, but I got to be honest with you. Besides Saxon, I don't think I've ever seen another textbook do it that way. So I'm not going to teach it that way. Good. All right. So the idea is that this is the goal, the objective, because when you get to that, it's arcsine or inverse sine of u, and we're good. Okay. So really the meat of the problem is, how do you make the problem you're given make it look like that? The first thing is the negative out front. That can definitely be brought out front, or the negative up there, that can be brought out front. The first thing you should focus on is the 7. You want that to be a 1. How do you make it a 1? Yeah, you pull out a root 7. So I'm going to pull out both a negative from the top and a root 7. When you do that, the numerator is now positive x squared dx. And the denominator, it's going to change substantially. The denominator root will be 1 minus 4 sevenths x to the 6. Very cool. Praise compact. All right then. Once you have that 1, then you can find u squared. U squared, and I do take the time to find u squared. I don't just go straight to u. I go u squared is 4 sevenths x to the 6th. Therefore, u is what? 2 over root 7 x cubed. Perfect. All right. And as a consequence, du then is what? 6 over root 7 x squared dx. Oui? Yeah. All right. So now what should I do? I typically isolate the x squared dx. Okay, so that's up to you, but x squared dx is root 7 over 6 du, yeah? Yes. Now we're ready to plug and shove. The negative 1 over root 7 is still there. When I sub in for the x squared dx, it's going to get replaced with a root 7 over 6 du. And that root 7 over 6 I'll put out front. The du, obviously, you have to put in the integral. You with me? The inside of the root is 1 minus u squared. So the cleanup of the constants amounts to negative 1 over 6, yeah? And the antiderivative is arcsine or inverse sine, whatever you want to call it, of u. And I typically don't write the u, I just replace it at the same time. The u, back in our original work, was identified as 2 over root 7 x cubed. You with me? Okay. We'll practice that a couple times more before I lay it on you on a test. It does take a little practice. Second semester, we'll actually approach that in a different way called trig substitution. But for now, that should be cool. The other ones, I feel like they should be a little cleaner. And so I'll let you work on those. Feel free to talk them over. We'll go over them that. Never everybody's close to something. By the way, that 13 we just did, that's a replacement problem. So when you go to break your whole, don't expect that to match.
how you totally can't. They're not the same. How are you about that you can serve the denominator?
Are you allowed to?
It just can. Totally split up the new down first. Hey, permite. Permite.
But they're not the same, right?
Yeah, row 7 set of confidence.
You only do one side. So even if it wasn't just one side, you just went for a 6.
I missed the day of that. And I finished last night.
Yeah, you weren't here.
I made the decision to go to very close, but
A real big number to move the tree for you. What's your setup? I'm still getting with the setup.
just want to share my statuses on different maps that I haven't taken. I've included those.
Ready? How are you doing? Done?
Yeah,
All right. So yesterday we talked about odd powers of trig. I know it's actually an even and an odd power of trig, but you identified that as an odd power of trig problem. What do? What's the strategy? Take out a cosine. And by the way, I'm going to show every little step, but you could definitely take a few liberties or skip a few. Then what? Okay, and I have identities for both of those. Does it matter which one you replace, or does it have to be the cosine that gets replaced? It does kind of have to be the cosine, and the next step goes to why that is. You can actually sub now and do algebra, or do algebra now, then sub, whatever you prefer. It's up to you. But the reason is that the whole strategy you're trying to get to is a u sub strategy. And that single will become your du, and if cosine is du, then everything else has to be solved. So if u is, what'd you make u? Sine of x, and you do your integration, what was your final answer? Something like 1/3 sine cubed minus 1/5 sine to the fifth plus c. Okay. This time you didn't pick up a negative because the term was positive. Is that one okay? Okay. All right. Students at your level don't usually make this mistake, but just to be sure, very similar but totally different strategy. What's the strategy on the first integral? Split it up. You can split a numerator sum up and integrate. So this would be 1/2 x squared plus natural log of the absolute value of x plus c. Yeah. Can you split a denominator sum up? Okay, so what's the strategy there? U sub, yeah, u is x squared plus 1, du is 2x dx, and so you have something like 1/2 du over u, so you get something like 1/2 natural log of the absolute value of x squared plus 1 plus c. Tell me why the absolute value is not really necessary. X squared plus 1 is positive. Take that first idea and tell me, how would you integrate that? The AP exam practically never throws this kind of question on there, but it's very common in college classes. I don't know why. Can you see that? How would you do that? Is it USO? It's not USO. Okay, so how would you do it? The answer's right there. How'd you do it? You split it up, and you didn't really split it up, you divide it, right? Okay, so what should you do? You should divide. And that's where those long division skills, you either can synthetically divide or long divide. The first step there, before integrating, is you have to divide it. And you get something like, do you remember your division skills? You better, because you're going to need them for sure. X and x squared, x times. Multiply, record it here, and subtract. So you get something like negative 5x plus 3, x into negative 5x. Negative 5 times, negative 5x minus 35. Change signs, draw the line, 38 plus 38 over x minus 5. Therefore, this integral is equivalent to the antiderivative of x minus 5 plus 38 over x minus 5. Then you go term by term, 1/2 x squared minus 5x and y. Oh, so are you dividing by x plus 7 or x minus 7? Oh, yes. Sorry, that's not over x minus 5. Yeah, yeah. Sorry, I don't know what I was. Yeah. Yes, thank you. I don't know what I was talking about. Yes. Okay. Are we good? Okay. This one, this is. You're just learning this, and so hopefully it's going well. Where did you draw your origin? At the lower left side of the. Did you even draw a picture? Okay, if you need to identify your axes and your origin. So if you draw the origin in the lower left quadrant, or lower left corner, then it's all first quadrant. This is 10, this is 10. I read carefully and say it's filled. That's important. It's filled. And I want to know how much force the water is applying to one of the faces. And so, force is the sum of many what? Rho dAs, or PDAs if you like, okay? All right. I still look at this and think homecoming dance. It's the sum of many PDAs, you know what I'm saying? But rho dA, all right? The rho is 9,800. The D, you're about to get confused, but right now that D stands for depth. Okay, so the depth of each slice. So when I draw this slice here at 1, how deep is it? How deep is that slice? 9, okay. When I draw this slice at 2, how deep is that slice? 8. So would you agree that any time I have a slice at y, the depth is 10 minus y to the depth, all right? The distance from the top to the bottom, upper minus lower. So 10 minus y. What about the A? Does that stand for area of the face? No, it stands for area of the slice. What's the base of each rectangular slice? 10. What's the height of each rectangular slice? And what are the units or limits of integration? 0 to 10. And what are the units once you punch that in? Meters. Okay. Now the unfortunate thing is that today's lesson is going to be very similar and people get the two confused. And so I want to take 2 minutes maybe to really solidify. I understand you've only been doing it a couple of days, but I really want to talk about a fluid force review before we go on to work, all right? So in every case, the force on these vertical faces is rho dA, all right? And the rho is always constant. The depth is always the surface of the fluid minus y, wherever the surface is, and that would be based on wherever you put the origin. But the area, that gets a little complicated. The area could be one of three different things. In this case, the area is a rectangle, and the base is always the same. The base is a constant, and the height is dy. You with me? Sometimes you'll get a non-symmetric face like this. In this case, when you do the area, the base isn't constant of those rectangles. The base is varying, and that means it's a horizontal distance. And we'd have to then replace x with some kind of relationship of the border. Okay, the x gets replaced by really the shape of the figure itself, whether it be circular or triangular, in which case you're looking at linear here, linear replacement to x. You with me? Then you have the possibility of symmetry. You could have a trough like this, in which case the area, instead of bases being constant, or the bases being 1x, the bases are 2x's and dy. But again, you still have to sub for the x. Now, the beauty of, I had a student in the last class saying, so do I have to, when I go to sub this, do I need to use absolute value for the shape of the relationship? And that's actually very logical. You're thinking, oh, here, that's an absolute value graph. That's not necessary. You're just looking at this relationship, and this side's taken care of. How? By the 2. Yeah, the 2 is taking care of that. You're just looking at linear, so don't overthink, all right? That would be the same case if you did this. It's still a symmetry case, and the area is still 2x. The only difference is the xy relationship, instead of a linear one, would be a circular equation. You follow? All right. Let's go to work. Generally, physics people, how do you find how much work is done? Force over distance, yay. Now, would you think of that or conceptualize that as this? Is that how you would write that? I'm not a physics person. Yes? Yes. Okay, cool. I'll build off that. So, force over distance, cool. The amount of work, though, we're not just doing work, generally speaking, we're doing work specifically to work required to pump a fluid out of a container, all right? So it's a kind of a specific condition of work. It's pretty much the same when you move anything vertically is what we're going to do here. But check this out. So you're trying to empty a container of fluid. And think of a person sucking some stuff out of a cup or a straw, or whatever, using a straw, all right? So here's the base case. Here's a person emptying the typical thing we use to hold liquids is a cube, right? You'll be grateful for it later. All right, this person, does this person do more work or less person than person A? More. Why? I should make somebody actually get on the table and try and suck some fluid out of the cup from way down. That'd be good. Do that. Okay. So that's a lot of work, yeah? Okay. What about instead of water in the cup, they have mud or a milkshake, maybe better, or a smoothie or a really thick. More work or less work? More. Okay. And then this guy's front face is the same as this guy's, but this guy's container, like again a normal container, is a really long rectangular prism. Who does more work? Okay. So that said, then. The main variables that work here, when we go to figure out how much work does it take to get this fluid out of that container up over the top edge, depends on three things. Give me the three things in here and here. Distance, the distance over which you must pump the fluid. What else? I heard somebody say. The density, yeah. The density of the fluid means for more work. And what else? The third condition. The volume. How much needs to be pumped. Now, in terms of math relationships to work, are those direct or inverse? Let's go with distance. The greater the distance, the greater the work, or the greater the distance, the less? The greater. So that's a direct relationship. What about the greater the density, the greater the work, or inverse? Direct. Direct. Okay, and what about volume? Direct or inverse relation? Direct. So it's 3 direct. That means joint variation, which is to say work depends on distance, density, and volume. Now, just to tie in with exactly how this corresponds, it actually makes a great deal of sense. First of all, if work depends on force over distance, the first thing we're going to do is say, in math, we call a vertical change delta y, not delta x. In fact, let's just use distance. Okay? Now that distance, usually they're going to have you pump the fluid out of the container only over the top edge. So rather than this huge distance, it's just how much work is required to take it out of the top edge. You know, you want to use as little work as possible, and you wouldn't pump it further than you had to. So that distance will represent the distance from some level up to the container top, not the fluid top. The force, well, how much force is required? Each of these layers, won't that be at a different distance? Won't I have to pump this layer further than that layer, right? In fact, every one of these layers has a different distance. So instead of a straight up algebra calculation, it's an infinite sum calculation, because every one of those distances is every microscopic differences in change in y. So it's going to be a dy calculation. Last but not least, the force. The force will depend on how heavy the stuff is and how much the stuff is. So force will depend on rho and the volume and the distance. Now the volume, that's where your differential is going to come in. It feels like that distance is your differential. It's actually not. It's in the book. Why this requires calculus then? It's because every one of these layers of fluid needs to be pumped at different distance, and so that's why an infinite summation. We're really pumping infinitely many sheets of fluid up and out. Each of those little sheets gets moved to different distance. Cool? So let's look at this in action. A rectangular prism with base 8 by 6 and a height of 10 centimeters is filled with water. How much work is required to pump the water out of the top edge? So let's put our origin at the bottom edge. And this, I'll call this 8. Now, and the height is 10. Now, in the force problems, I didn't even consider how far back it went, because it wouldn't matter. It wouldn't matter if this went back 6 meters or 1,000 meters. The force on the front is the same. It didn't matter. But for this, that will matter, because that goes to how much volume we're going to have. That 6 will matter now. So you need that. And we're looking at something like that, yay? All right, so let's talk about the process. Work is weight density, distance, and volume. The weight density, because this is water, the weight density is 9,800 newtons per cubic meter. Cool. The distance. Let's say this slice at 1 meter. How far do I have to pump it to get it out of the container over the top edge? 9 meters, right? And this one at 2 meters needs to be pumped 8 meters. So the distance is always 10 minus whatever the y is, yeah? Okay. The volume. The volume of each of these sheets. What's the volume of each of those sheets? 8 by 6 by the height. Now, what's the height? The differential, V1. All right. And then the limits of integration? 0 to 10. All right. Now, don't worry about putting it under your calculators. I'm not sweating it. Let's go through with units, please. What are the units on the weight density? Yeah. Oh, yeah. Sorry. Oh, shoot. Good call. Half filled with water. So, didn't even see that. Does that affect the limits of integration? It does, because I only have to pump that 5 meters, not the top 5 meters. So you're absolutely right. Thank you, Brady. Does that affect the distance, 10 minus y?
Yeah, or no.
Okay, so now here's one of the differences between force and work. When it's about force, it's about the surface of the fluid because depth is the issue, and you gets reference to the surface. But when you talk in work, it's not getting to the surface. I'm not trying to just take this layer to the surface and dump it. I'm trying to take that layer all the way to the top of the container and dump it. And so it's about top of the container. So that does need to be 10 minus 5, not 5, right? Units now. Thank you for saying that. I didn't obviously read the problem carefully. What are the units on the weight density? Newtons per cubic meter. What are the units on the distance you pump? Meters. What are the distance? What's the distance? The units on the 8 meters. What are the units on the 6? What are the units on the dy, the height? Meters. All together, then units are Newton meters, which is work, joules. The units are Newton meters, which is joules. Okay. All right. Let's try a little harder one. Instead of a rectangular prism, we've got a little more action one. So the water contained below is filled to a height of 2 meters. This is 2 meters. If the weight density of the fluid in newtons per cubic meter is 8,000, find the work done to pump the fluid out of a small hole in the top of the container. There's some hole right here, and you're just pumping it out there until it's empty. All right. I was at the school I went to. You always wrote the formula just because, if nothing else, the more you write it, the more it'll get into your brain. So, rho, distance, volume. The rho is 8,000. Cool. Now, before I do anything else, I guess I'm going to need to draw a picture. Where shall we place our origin? At the bottom of the circle or the top of the semicircle, I should say? At the top of the semicircle. Okay, consider the consequences of the bottom now here. Looking ahead into the problem, right? The volume of this is going to be something like 2x here, dy here, and 12 there, right? And then what do you reckon you'll have to do? You have to sub in for x. Okay, you have to sub in for x because you're integrating with respect to y. Now, if the center, if you put your origin there, what's the equation of that semicircle or circle? X squared plus, this is 8, so this is 4. So give me the equation. 8 plus, or x squared plus y plus 4 or minus 4?
Y plus 4.
Oh, we're a little rusty on the old circle equation. We need to review. X plus 2 squared plus y minus 3 squared equals 25. Where's the center of that? Negative 2,
So it's minus.
positive 3. So this should be minus. But my point is this. Now you're going to have to solve that for x, which isn't terrible. But if you're integrating this by hand, it's terrible. And so you never, on a circle case, you never want the origin anywhere but the center of the circle, because that's going to make for the cleanest equation. So if you drew that, I apologize, erase that, and we're going to put the origin at the center of the circle. The diameter is 8, so the radius is 4. This goes back 12. I'll need that when I get to the volume. Here we go. Okay. So then, the thing is, it's only done to a height of 2 meters. So where's the top of the fluid? -2. Okay, cool. So now we're rolling. Let's go to the distance. What's the distance you have to pump the fluid? Negative what? Okay, do you need, so let's, if you get confused, this helps me a lot, because these kicked my butt when I was first learning. Say you have a slice at -3. How far do you have to pump it to get it out? 3, okay, so what's that? It's the opposite of the y. Think upper minus lower. The upper you need to get to is 0 minus y. Okay, 0 minus y, upper minus lower. Something like that, right? What about the volume of each? Now again, I'm talking the volume of the cylinder. I'm talking the volume of these rectangular prisms. The width is 2x, yep. The length is 12, and the height is dy. Limits of integration. -4 to 0, 0 to 4, 0 to 2, -4 to -2, -4 to, do you need to, now here, is this about where the container is or just where about the fluid is? Just the fluid. I only need to pump where the fluid is, and that's from -4 to -2. All right. Last but not least, we need to replace the x. What's the x? The x is just how far you went to the side. And that how far you went to the side is when you end on the circle. So when I say, what's the relationship? It's the boundary relationship. What's the equation? X squared plus y squared equals 16. Therefore, x is, we'll just go with the positive because we have put the 2x to get to the left side. So just positive square roots of 16 minus x squared. And feel free to combine some constants or pull all the constants up. The units again are? Joules. Okay. You'll get really large numbers for these, by the way.
Oh, yeah.
I did, what did I do?
In the last thing, you said 16 minus 6.
Here?
Well, yeah, they're also in the integral too, though.
Oh, why is it that?
Should be 16 minus y squared.
Oh, yeah, sorry. Thank you.
You have an extra 2 in your equation.
I do? Where?
You combine.
Oh, because I did. Okay. Wow, sorry. Just testing you. You passed. Good job. Y squared. Yeah, thank you. You're an excellent critical thinker. Way to go. You'll be an excellent wife someday. You'll criticize. Catch those mistakes, baby. All right, so here we go. Compare and contrast work versus force. When you go to do force, it's row depth, D for depth, and area. I just care about what's on that face. I don't care about how far it goes back. You get the same amount of force on the face whether it goes back 1 meter or 100 meters. Doesn't affect it. Okay, the limits of integration are still from fluid low to fluid high. It's the force is where the fluid is, and so your limits of integration should focus on where the fluid is. When you go to work, it's row distance volume. Now, actually, I should have said here, depth. When I say depth, is that relative to the surface of the fluid or the top of the container? If I said, here's some water that's 4.8 here, how deep is this slice? It's 3, here's the surface. How deep is it? 3. It's 3 deep. So wouldn't you agree that it's relative to the surface of the fluid, not the top of the container? So when I say depth, it's surface minus y, not about the container. When I do work, that distance, that's usually to get to the top of the container. I don't want to just get it to the surface level and dump it, because that would just be refilling it. So it needs to be the container top minus y. And the volume, it has all the components of area, same as area, but it also includes times how long the container is, the length. Right? The limits of integration are still about where the fluid is. You're only pumping where the fluid is, so it's still fluid load, fluid height. Don't get the container into it. I don't need to pump empty space out. It's just where you're doing the liquid pumping that you need to have all this being done. You with me? Okay, so let's try this. A trough with a triangular face. Top edge 3 meters, side edge, that's, I mean this edge, the vertical edge is 4 meters. And height 7, or maybe not. Top edge 3 meters. Maybe I mean this. What do I mean? That's probably what you want to know. What do I mean when I
I
mean
like how like wide it is.
height? So this is 7?
Yeah.
And this is 4?
Yeah.
Okay. All right. I agree. All right.
Like,
Is filled halfway with gasoline. Find the force the gas exerts on the face. Find the work required to pump the gasoline out of the hole. Now, if you draw your origin here, then aren't we going to have a second quadrant kind of situation? So question, is there any reason we can't just mentally flip it over and look at that? Would the work be the same? Yeah, and the force would be the same, so let's do that. Let's be first quadrant people. So we have a 3 here, a 7 here, and this goes back 4. All right. So the first question is force. Would you try the force calculation? That's review, so hopefully that'll go well. Try that on your own, and let's see how that is, if we agree. Is it filled? Halfway up. It is?
what?
Is it the-
Where's the difference?
halfway up? Isn't mine filled halfway up? Are they different? Oh, it's formatted differently because I pasted it in and it got too big, but I think it's the word's the same.
Well, it says option for the 16
Oh, yeah, you're right.
and this is height 7.
You're right. Did you already start the way I have it?
Yeah.
Okay, you're right, Brady, sorry. So it reads like, yours reads like this should be 7, yes?
Yeah.
Will you just scratch it out? Just forget the words and just look at the picture, sorry, I'm sorry. I sometimes I'll make changes to my note sheet, but forget to make changes to my overhead.
Wait, what's the difference?
On your paper, it says 7 is the distance between the bases, which means these are the bases, and that would have to be 7.
Yeah, but
So it's half filled. While you're working, what's your depth? 7 minus y or 3.5 minus y? 3.5 minus y. Area, constant base, varying base, tube varying base, symmetric, whatever. Varying base, so x dy, yeah? What does x get replaced with? 3/7 y. I agree. The equation is y equals rise 7 run 3x. So switched, it would be x equals 3/7 y. Limits of integration? 0 to 7 or 0 to 3.5? And what are the units on that once we get our answer? newtons, okay. Try the work if you haven't already done so. Now you're pumping the fluid out over the top edge of the container until it's empty. Ready? Distance. Work is about distance. What's the distance? 3.5 or 7 minus y? 7 minus y. The volume has a lot of the same components. Doesn't it still have this x, which translates into 3/7 y? And the height is still dy. The only thing it has on top of that is the 4. That how far back it goes matters for the volume. And limits of integration. 0 to 7 or 0 to 3.5? Still 3.5 because it's about where the fluid is. We're only pumping the fluid out, not the air on top out. And that's it. What are the units on that? Okay. Are you getting the gist? Should we go through another example, or you're starting to get it, or you got it? Move on to questions. Talk to me. What?
We should do this.
You get it? Okay. All right. We will go over it a little tomorrow. I think I might hand out. I don't even know if I have to look at. I don't even know if I need to teach 78. It's about motion, which you know a ton of. I'll look at it. But we'll have a lot of time for catch-up tomorrow and Friday, so if we want to go back over that, we can. Questions on homework 70, what do you have? 75 or 6? 75 and 76. Give me 75 this or 76 that. Oh, we were going to talk about the revenue maximization. I'm going to make that my warm-up tomorrow. We will talk about it. Okay. All right. Give me what you got. 75 this or 76 that? Any questions? 7610. Let's start there. 7610. Okay. 7610. Is that replaced or straight up out of the book? It's replaced. May I look at your paper? Oh, yeah. That's a good one. Oh, good one. Way to go, me. Okay. So, if I say, what's the derivative of sine in radians, you would definitely not say cosine, because it's not. Okay? Now, think magnitude of the numbers involved. I imagine Miss Cannon, when she taught the derivative of sine, she might have done something like this. And this is pi over 2 and 1. And if you, that's about 1.5 here, right? So this would be 1. Now, if you drew a tangent line on that graph right at 0, you would actually, if you did it really beautifully to scale, you would see that that slope there is exactly 1. And if you then recorded that, the slopes, which is to say the derivative of sine, and kept doing it, then you would say, all right, at pi over 2 it's 0, and at pi it's negative 1. You start to discover, whoa, in radians, when the units are radians, the derivative of sine is cosine. Now imagine then, instead, I drew it on a degree scale. Here we go. Here's 1, and here's 1 unit here. Now, if I go on a degree scale, In degrees, where's the max? What degree measure is the sine pcat? 90, okay, so that's... Okay, so I'm imagining somewhere in the math closet over there is 90, all right? Now, if I drew that curve, I'm rising way too fast. It's actually got to be more like, okay? That's the sinusoid. It's a wave that's so long it's into the math closet, right?
Yeah.
Now, if I graph the slope here, what's the slope? Is it up 1/1? No, not even close. It's way, way flatter. How flat? What's the slope then? It's actually about 160. It's that flat. Or pi/180 flat. Okay, now that's why all of calculus is done in radians, because the units in radians are more like a one-to-one measure. But if you talk degrees, then the important points in trig are so spread out that all your calculus derivative rules are just blown away. Not true anymore. And the derivative of sine in x degrees is not cosine. You would have to really find it by saying, let me convert x degrees into radians. What is x degrees? What's the conversion rate from degrees to radians? 23 degrees is, there's a lot of conversions rates, but I do that one, right? So x degrees is actually pi x over 180 radians. The derivative then is pi 180th cosine of x by chain. Okay, bye. Have a lovely day. Oh. Nah. Not even 75? You guys are weasels. Weasels. All right, fine. Have a time for me. I love it when I get tons of stuff from weasels.
I love it. I don't.
All right. Have a lovely day.
Wait, Alex.
Have a great day.